Hi guys, today we're going to take a look at the overload calculation of a small 1.3 kilowatt single phase capacitor start motor.
So let's start with the control circuit for a DOL motor. So I'll normally put it on a 1 amp circuit breaker. This normally won't be too much for the magnetizing of the contactor. Then you'll come through the normally closed of the overload, the normally closed of the stop button. Then you will push the start, right? So it'll flow like this, and then it'll energize your contactor. You'll have your centrifugal switch obviously in a closed position. It's actually normally closed. Your capacitor and as well as your auxiliary winding, this will all kick out after startup. All right, then you'll just stay with your running winding normally. Sometimes they've got the capacitor run one, which is actually a little smoother for me. But whichever way, this should be pretty much the control circuit for DOL. All right, after you release stop button, this piece over here will disengage. It'll be normally open again, but this one over here will close and current will still flow. The only way you'll break that is with the overload, will kick out the contactor, or your stop button will kick out the contactor. I know a lot of my friends will be like, why are you showing me such stupid, like basic electrician stuff? But I mean, still, people get confused about things sometimes. And I'm pretty sure like everyone probably knows the stuff, but maybe they don't. All right, so today I went to a motor and it was 1.3 kilowatts. I'll be using that as an example. All right, so this 1.3 kilowatts is its output shaft, right? It doesn't actually tell you how much power is going into it. It's telling you how much you will get out of it, which is obviously a more moral way to rate them, but actually makes it harder for the people putting protection in. All right, so electrical is what we want. It will be basically the output plus the losses, or electrical will be then minus the losses will be the output. Efficiency of around 90 on these motors, 90%. You'll take your output kilowatt rating and you'll divide it by that 90. End up with 1.4 kilowatt. All right. So then you use the single phase power equation with an average power factor of these being a 0.85, and you end up with your ampacity that you're actually pulling nominally, which is 7.388. Okay, so basically when the motor isn't running at its nominal ampacity, there's normally either resistance or a fault. So that's why in industry, we normally use a factor of safety of 1.25 on the overload. So they'll normally start up at 5 to 8 times the rated capacity at startup, but no worry, the overload does compensate for this. It is particularly built to withstand this at initial startup and then check for a fault after startup to save the motor.
On a standard overload, you do have the normally closed, normally open, so you'll be wiring through this normally closed, which you've got to set now to the amps, and if it goes over, it drops out your contactor, 6 to 13 MCE.